Hello biology students, and welcome to video 3 of the inorganic chemistry unit, where we're going to be talking all about water. So before we jump into this video's material, I want to remind you of one thing, and that's the fact that if I have a molecule with covalent bonds, so maybe something like water, remember that the electrons in each of these bonds, there are 2 electrons that are being shared. Because remember, in a covalent bond, atoms share electrons. Okay? So I just want to remind you of the fact that each of these bonds has 2 electrons that are being shared in each one. Okay? Turns out there's different types of covalent bonds. We could have a molecule with non-polar covalent bonds, so a non-polar molecule, and this means in that bond, the electrons are shared equally. So maybe if I had a molecule like oxygen gas, so here I have a double bond. Remember, in a double bond, there are 4 shared electrons. In this case, this oxygen and this oxygen are sharing the electrons equally. You can kind of think about the electrons are like in the middle of the bond, if that helps you to think about it that way. However, in a polar covalent bond, what actually ends up happening is the electrons are not shared equally. So an example of a polar molecule is water. And it turns out the electrons in each of these bonds end up hanging out a lot closer to the oxygen than they do to the hydrogen. So that's a polar molecule, a molecule with unequally shared electrons. Now, I don't want you to be confused. Now, even though we know water is a polar molecule, so it's not sharing electrons equally between the oxygens and the hydrogens, it's still neutral, okay? So that being said, water still has 10 protons and 10 electrons, and those 10 positive charges cancel out the 10 negative charges. Now, how did I get to that 10? So remember, water is H2O, okay? Now, the oxygen, remember, oxygen's atomic number is 8. Which means it gave us 8 protons and 8 electrons. Then each of the 2 hydrogens, their atomic number is 1. So each hydrogen donated 1 proton and 1 electron. So it's a neutral molecule. However, that charge is not distributed equally. The electrons in those bonds are closer to the oxygen molecules than they are to the hydrogens. And you'd be wondering, well, why is it closer to the oxygen? Why don't the electrons hang out closer to the hydrogens? And that's because oxygen has 8 protons. And you can kind of think, if you're an electron, you're negatively charged. And you're going to be really, really attracted to protons because they're positively charged and opposites attract. So therefore, these electrons that are hanging out in the bonds here, the electrons right here in these bonds, they're more strongly attracted to oxygen's 8 protons than it is to hydrogen's measly 1 proton. So they end up hanging out much closer to the oxygen more often. Okay, so what? Why do we care that the electrons are hanging out closer to the oxygen? Well, you can kind of think, you have these extra electrons that are closer to the oxygen molecule than to the hydrogen molecule. So what that means is the oxygen, this end ends up with a this end of the molecule ends up with a slightly negative charge because the electrons are hanging out there more often. And similarly, the hydrogens end up with a slightly positive charge. Now, it's not a full charge. We actually label it with the weird S symbol, so like a little S symbol minus, S symbol plus. That means it's partially negative. So this end is partially negatively charged, and these ends are partially positively charged, okay? And that partial negative and partial positive charge gives water a lot of really cool properties. So, for example, if you kind of think about it, so here I have a water molecule, and remember I said the oxygen is slightly negatively charged, and the hydrogens are slightly positively charged. Now say I put it near another water molecule. Here's my other water molecule. Remember, the hydrogens here are also slightly positive, and the oxygen here is also slightly negative. So what's going to happen is this hydrogen right here in this water molecule is going to be, and it's slightly positive, so it's going to be attracted to that slightly negative oxygen, and it will form a really weak bond. And that bond we call the hydrogen bond. So the partial positive and negative regions on 2 different water molecules attract one another, and it kind of makes water sticky. Water molecules stick to other water molecules because of these hydrogen bonds that are formed. They're weak bonds formed between the hydrogen on one molecule and a negative oxygen on another molecule. Now, it doesn't have to be oxygen. Any molecule in a polar molecule, it could be attracted to as well. Okay. So this polarity and hydrogen bonding that water can do, it's really, really important, and water can do it a lot. In fact, a single water molecule can be involved in 4 hydrogen bonds with other water molecules at any given time. Okay, so we already know water is pretty unique. It's one of the few elements that in nature, so naturally, not in a lab, exists in all 3 states. It can be a solid, it can be a liquid, and it can be a gas. Water has properties. So for example, here's a list of all the properties that water has. And it turns out that all of these properties are all due to the fact that water can form hydrogen bonds. So water is a polar molecule, and being a polar molecule allows it to form hydrogen bonds. Okay, so let's look at these properties a little bit. So the first property listed there was cohesion. And basically, cohesion is the attraction between molecules of the same substance. So that's one we kind of already talked about. So the fact that water sticks to other water because it's forming hydrogen bonds, that's cohesion. You can kind of think, if you had, you just waxed your car and it rains, you can think all the water forms little bubbles on your car, and that's because the water is attracted to the other water molecules from the rain, and it sticks together. This is cohesion. Okay, so cohesion leads to another property called surface tension. That's pretty important too. So I like this picture here. You can see this bug, right? He's walking on water, and the reason the bug can do this is because all the water molecules that he's walking on hydrogen bond to each other, creating, a solid surface for the bug to walk on. In other words, the pressure from the bug pressing down on the water is less than the strength of the hydrogen bonds holding the water together. This is the same reason why if you had a wine glass, you could overfill it. You can see, the glass ends here, but the water ends here, because the water is sticking to itself through these hydrogen bonds, allowing the water to rise up higher than the glass itself. So another kind of similar property is adhesion, and this is where there's attraction between molecules of different substances. So in this case, the water is hydrogen bonding to something else. So a kind of a famous example here is the formation of a meniscus. A meniscus is this little curve here. And what's happening is water is polar, so it has that slightly negative and slightly positive end on the molecule. And for whatever reason, the glass of this graduated cylinder also has a charge. So maybe let's just pretend the glass is negatively charged. So if the glass is negatively charged and I have some water molecules in there, you can kind of imagine that the positive ends on the hydrogen can hydrogen bond with the glass itself, right? Because this positive hydrogen will be attracted to the negative glass. So what that means is the water literally sticks to the glass and almost climbs up the sides, creating this curve called a meniscus. Okay, so if we put the properties of cohesion and adhesion together, we get a property called capillary action. And I promise you, if it were not for capillary action, it would be very, very hard for humans to survive on this planet. So capillary action is where you get cohesion and adhesion working together, and it results in a liquid rising up some kind of tube. Okay, so an example might be, or the most important example for us. So say we have a tree. So I'll draw a picture of a tree over here, and the tree has roots. Okay, so there are these little tiny tubes inside the tree that the water travels through. Obviously, I'm drawing a much bigger tube than it actually is, okay? So the water enters these tubes and the roots in the ground, okay? And then the water will adhere. It will use adhesion to stick to the sides of these tubes, and it will use cohesion to stick to the other water molecules. So by sticking to the sides of the tube, it can almost climb up the tree, right? And by sticking to the water molecules behind it through cohesion, it can pull those molecules up the tree. So at the top, we're going to have branches, and if it's really hot, the water is going to evaporate out of these branches. That process is called transpiration. And as water evaporates out, it pulls the water behind it up. So that's cohesion, and again, the water can stick to the side of these tubes through adhesion. So those two things put together are called capillary action, and they allow basically plants to take in water and release them into the atmosphere. If it weren't for this, plants wouldn't be able to get water very effectively, and we wouldn't have any vegetables to eat, which means all of our livestock that depends on plants also wouldn't be able to survive as well. Okay, so the next property that water has that's due to hydrogen bonding and polarity is temperature moderation. So you can kind of imagine if I have a water molecule and it's hydrogen bonded to this water molecule and it's hydrogen bonded to this molecule and those are hydrogen bonded together, this water is going to be pretty hard to disrupt. So say if I wanted to heat up this water and make it evaporate, I would have to break all these hydrogen bonds. Because what happens when something evaporates is all the molecules separate apart and become a gas and spread out from one another. So this means that I have to put in a lot of energy to break those bonds. And in this, what that means is I have to put a lot of heat in to break those bonds. So therefore, water can absorb a lot of heat. It has to absorb a lot of energy to break the bonds. And this means the oceans around us change temperature really slowly because we have to put a lot of heat into, a lot of energy in to change the temperature of that water to break those bonds. And this stabilization of water temperature allows life to exist. You can kind of think if the temperatures of the oceans change dramatically all the time, aquatic life would have a really hard time surviving, and therefore we would have a hard time surviving. Okay, so these two examples, coastal regions, mild temperatures, and evaporative cooling, I'm going to save for class time to talk about. Okay, so finally the next property is density. So you might know that normally, in a normal situation, a solid would have particles very close together in a nice orderly fashion. A liquid would have particles that are moving a little bit faster and they're further apart. And then usually a gas is when you see the particles moving the fastest and having the particles furthest apart. But water is really strange. And water is one of the only substances that its solid is actually less dense than its liquid. So in other words, the molecules in the solid are further apart than liquid water. And that's kind of funny. And again, it turns out the reason for this, again, is all due to hydrogen bonding. Because what happens, and you can think in a solid, the molecules are moving much more slowly, right? Because at a solid, things are cooler, they're moving more slowly. And because they're moving slowly, that allows more time for hydrogen bonds to form. And when hydrogen bonds form, the molecules spread out a little bit and they form this kind of crystallized structure that has more empty space. Similarly, when something's liquid, it's moving more quickly. And when something's moving more quickly, it's easier to break the hydrogen bonds, which means they don't have this crystallized structure. And this means liquid water is actually a little bit more dense. And you might be wondering, well, why in the world? And the reason is because solid water is less dense than liquid water, it means ice floats. And that is so important. So the question I'm going to leave you with in this video is I want you to think about, why is it important that ice floats? What would happen if it sank? And how would that affect whole ecosystems and humans on the whole? Okay, so I'll see you in video 4, and that was video 3.